Here's a fluid mechanics question that looks at a non-inertial frame of reference, which has the form of a spinning tube, and then there are two manometers attached to that tube where there's some water, and then knowing the pressures or being able to read what the manometers tell us, we have to find out what is the angular velocity of the tube. Now, this was actually a problem that was given to students sitting the Physics Olympiad many years ago. And if you'd like to see anything similar on the channel, or if you have any suggestions for any problems that you'd like to see, please let me know in the comments. So let's try to understand what's going on. As I mentioned earlier, we're dealing with a tube filled with water, and this tube is rotating about an axis, and that axis is labeled this O and O prime, like this. And we don't actually know what the angular velocity is, but what we do know, or what we're told we know, are the two pressures P1 and P2, which correspond to two manometers situated at a distance R1 and R2 away from the axis of rotation. So let's see how we would approach this, seeing that we're dealing with a non-inertial frame of reference. And the way in which I'll do this is as follows. I will, first of all, take a random distance or an arbitrary distance r away from the axis of rotation all the way to here, perhaps, and I'll call this distance lowercase r, okay? And what I'll do now is I'll say that, okay, at the distance r, there will be a fluid element which is very thin, and we're going to look at the forces acting on that thin fluid element. So let's zoom things in a bit. So this is my fluid element, like this. Of course, this is infinitely thin, but I'm exaggerating with the size just to illustrate what's going on. So this has a thickness that I will call dr, okay? And it's located at a distance r away from the axis of rotation. Now, this fluid element will experience essentially two forces. Well, if we ignore the weight and we're just looking along the horizontal direction, it will experience two forces. The first force is going to be from this side, and that's going to be the pressure of the liquid situated on the left multiplied by the area, okay, where this A is the area of the tube. And then from the other side, there's going to be a different pressure. So I'm going to call this pressure P plus dP multiplied by A, like this. So this dP takes into account an infinitesimal change in the pressure with an infinitesimal change in distance going towards the right-hand side. And this creates a force imbalance because this force and this force are different from each other. And we know what that resultant force produces, and that is a centripetal acceleration, because this tube is rotating, which means that each fluid element has a centripetal acceleration pointing towards this axis of rotation here. So let's actually write Newton's second law in this way. So what we have is the pressure P plus dP times A. Okay, that's the force which has the same direction as the centripetal acceleration, and then we subtract PA, and that gives us the mass of this fluid element, which I'll just call dm for now, and then multiplied by the centripetal acceleration. So let's take this to the next page, and let's try to expand this a bit more. So first of all, you can see that PA and the PA from here cancel out, and we're left with dP times A equals dm times the centripetal acceleration. Now, we know what the formula for centripetal acceleration is, and that's omega squared multiplied by the radius. And the radius is essentially this lowercase r. So that is omega squared r. And the only thing left to do is to express dm in terms of density and volume. So this is what we will end up with. We have dp times a equals, so this dm is the mass of this infinitely small element, which is the density multiplied by the volume. And the volume is a times dr, right? Because this fluid element is situated within a tube, which is cylindrical, which means that this is also cylindrical in shape, which means that the volume is just the cross-sectional area multiplied by the height of the cylinder, which is dr. So that's multiplied by omega squared r. So the areas cancel out, which is nice. And this then gives us that dp is rho omega squared r dr, like that. So we've got two variables here. We have the pressure and then we have the radius, right? So what we can do now is we can actually find the static pressure as a function of r by integrating. So if we integrate, we have dp equals rho omega squared integral of r dr. And of course, you can take rho and omega squared out because rho is constant. We're dealing with an incompressible liquid, and omega is also constant. So if we integrate both sides, we end up with the following. So we have pressure, static pressure equals rho omega squared r squared over 2 plus a constant. So what we have to do now is we have to find what that constant is. And to do that, we're going to use the manometer readings. We're going to use one of the manometer readings, and I'll use the first one. You can use the second one, you'll end up with the same answer, but I'll use the first one. So here's what we have. At r equals r1, so when we change this r value to r1, our pressure changes to that manometer reading, which is P1. So we have P1 equals rho omega squared R1 squared over 2 plus C, which gives us C, essentially. So we know everything. Well, we don't actually know omega, but we can find the integration constant now. So that's minus a half rho omega squared R1 squared. Okay, so now I'll take this and I will put it in here. So we have pressure P equals, and I'm going to rearrange a few things slightly. So I'll first write P1, and then I have plus 1/2 rho omega squared r squared minus, and then this, which is 1/2 rho omega squared r1 squared, like this. Okay. So this is what we have to find. It's the omega squared. So what I'll do now is I'll use the reading of the other manometer. So at r equals r2, the pressure is equal to P2. So that tells us that P2 equals P1. So I'm just substituting, I'm replacing the P with P2 and the R with R2. So P2 equals P1 plus 1/2 rho omega squared r2 squared minus 1/2 rho omega squared r1 squared. So that is P1 plus, and we can actually factorize a few things. So I'll factorize 1/2 rho omega squared and then r2 squared minus r1 squared. And this should give us what omega squared is. So if we rearrange this slightly, we'll end up with omega squared equals 2 multiplied by P2 minus P1 divided by the water density times R2 squared minus R1 squared. And this gives you the square of the angular velocity, which means that if you actually want to find the angular velocity by itself, you can just square root everything and you get 2 times P2 minus P1 divided by rho and then R2 squared minus R1 squared. And that is the angular velocity as a function of the manometer readings as well as the locations of those two manometers. And the other thing you could do if you're interested is you can actually use this. So remember, this gives you the static pressure of the water within the tube as a function of the distance r away from the axis of rotation. If you want, you can plot it just to see how pressure depends on r, but as you can probably tell, it will be positive quadratic. And yeah, that is omega, and that's the end of the question.